Here's an intro both to the idea of parameterized curve in 3 dimensions and a particular applet. This is an MIT applet for looking at these curves. I won't show you all the features because we don't know what they mean yet. But the idea here is, well, let me show you one real crucial thing. There's a menu here, show curve input is where you want to start. And it asks you for x of t, y of t, z of t, t min, t max, and refinement. These three are the most important things. And you can either use the drop-down menu or just enter it in by hand. What they've got now is x is cosine of t, y is sine of t, z is t over 4. So just like a parameterized curve in 2 dimensions, and really just like a line in 3 dimensions, what we do is we have a time value, t, and that does not show up physically in the space picture. We have a time value, and for each value of time, we plug it into a function to get x. We get plug it into a function to get y, here sine, and we plug it into a function to get z. And then we just plot all those points and connect them with a curve. And the best physical model here is to think of the path of a particle as in time, like a fly buzzing around a room in 3 dimensions. And we've looked at that in the case of lines, and now we're just having the functions, instead of being linear functions of t, they can be nonlinear. So it's not really that different. Now, the t min and the t max, of course, are the start and stop. The refinement is just something about plotting it on a computer. That means there's 50 points it actually plots, and then it just connects them with straight lines. So it's not exactly a perfect curve. So you'd plot curve if you changed it, and then you go to vectors. Now, you want to click off if any of these are clicked, circle of curvature, acceleration, velocity for an A-frame. Click those off for now. You can, of course, play with them and try to figure them out. The main thing is position. Remember that even though we really are plotting the path of a point in space, we often promote everything to be a vector, and this position vector is just how to promote a point to a vector in the simplest way, which is make its tail at the origin. And so it's drawing this, and so you're thinking of it not only as a variable point, but also as a variable vector. That's useful because we're going to use vectors to describe everything like velocity and acceleration pretty soon with these guys. So, for example, if t, how long should it take to do one full loop around this? This is called a helix. Well, just about 2 pi, 6.28, and we notice that it's gone from down here up one level. And let's see if I can get it sort of looking around along the x-axis. Oh, not really. There we go. You can see it's over the x-axis now. Sorry, it's a little bulky when I'm recording. Okay. So let's look at just a couple of other examples of this. Suppose we put in something really simple. Yeah, let's see. Let's just put in t. This is a very popular example. It's called the twisted cubic. T squared, t cubed. Because there's no complicated functions here. Let's see. We probably don't need to go out to 4 pi. That's just going to make it really big. Now, one of the things here is the scale. Yeah, the scale here might not be very good. Okay, yeah. Once you screw up the scale on this applet, it kind of has a hard time recovering. But that's one thing, and I wish there were a zoom, but I don't think there's any zoom on this guy. So here's something, and I just want to point out something with this curve. I know it's not showing up incredibly well, but one of the techniques we're going to have for these guys, we had a technique with surfaces, with the quadrics, which was to reduce the dimension of the problem by slicing. Here, if you slice a curve with a plane, you just get a point. That's not super interesting. What you can do instead is project. And so if we look along the z-axis, we're just getting the xy picture. And that means we can't see the z-coordinate, so we're really looking at the parameterized curve t squared. Or in other words, y is x squared. And if you look at it sideways, that really is part of a parabola, y equals x squared. Now what if you look at along the x-axis, or let's see, along the y-axis, let's say. Then that's x and z. I claim that's exactly z equals x cubed, because now we're looking at t cubed and t. And it's a little hard to tell the difference, but I claim that is really a cubic. In fact, let's go from -1. That's going to make it more obvious. There we go. Now let's look along the y-axis. There we go. That looks like a cubic. It's backwards because the x is going this way. Maybe I can rotate it all around. Yeah, there we go. That looks like x cubed now. as soon as you put it in perspective, you realize, hey, it's doing more than that. It's doing stuff in the y, but if you really can't see what's doing in the y, it looks like x cubed. Now, if you look at it along the x-axis, it's most interesting. That's a funky curve because that's t squared comma t cubed. It's the simplest example is something with a cusp, and because here z is y to the 3/2 power. It's not as nice a power. So it's a good example of projecting things. Let's look at one more example. Let's look at, let's say, I'm not sure if it understands ln, so I'm going to put in log. It's not that different. Let's put in 1 over 1 plus t squared. Hopefully it'll actually enter that in. And then z equals, wow, that's slow. Let's say sine t. So I'm purposely putting in 3 different functions with rather different behavior to see these projections. And I don't want to do negative because that will kill the log. Let's do 0.1. And going to, let's say 6 to get 1 period of the sine function, mostly. Okay, so we're going to plot that sucker. Whoa, that's weird. Okay, so this is something that would be very hard to graph by hand, to be honest. Okay, but like with a matching problem, we could say, okay, suppose there are a bunch of options. We're going to do these kinds of problems. How could we match this with the data we've got here? Well, we could project. So, for example, if we look at just what it's doing, let's try to see just what it's doing in the z variable. So we're going to ignore the y variable for sure. We can still see x and z here, but at least we can just see what is it doing in z. Okay, it looks like it's bouncing back and forth in the z. It's bounded, it looks like, and it's bouncing, oscillating at least a little bit. Okay, that's plausibly the sine t behavior. Now let's definitely ignore x and look at y and z. We still see the oscillation back and forth in z, and now in y, what we're seeing is something that starts out here at a moderate size and then just gets smaller. And in fact, if we went further, what we would see is it just keeps getting smaller and smaller. That's what this thing does. As t gets bigger and bigger, the 1 over makes that get smaller. And then let's look at, well, we haven't seen the x behavior. Let's look at x and y. Okay. So here we're seeing the x behavior should be giving me starting out with negative numbers and then starting to be positive, and that's exactly what over this range of the t values. Log should start out negative, go through 0, and then end up positive. What other ones could we do? Well, that's probably all the really good ones. So let's go back to the default example. And let's do like 15 here. And this is a great example of using that kind of procedure. And here, it actually is really nice if you look at both x and y together. In the last example, none of the functions really fit together very well as a pair, but here's a great one, where if you look at cosine and sine, they're fitting together as a circle. That's how you parametrize a circle. If you look at just, let's say, x and z, you're getting a cosine wave, although it's kind of upside down. If you look at just y and z, I'm ignoring x now, you get a sine wave, although it's kind of upside down and backwards. And so sometimes, if these functions are good enough together, like with the twisted cubic or with this helix, you can just look at those projections and it will be a familiar shape. In the other example, where the functions were more random, it was a little harder to make the match, but we could still do things like look at, are things bounded? Are things positive or negative? Are things oscillating? Are things blowing up to infinity? Those are all good questions to ask and look at.